Hello guys and welcome. Today we'll be looking at fractions and we will start off by looking at simplification of fractions. And let's first look at an example working with normal fractions, and that is not an improper fraction. Let's have this example, 15 over 45. If we were to simplify this fraction, we will take like terms. So 15 is 3 times 5, and 45 is 5 times 9. And then, since both denominator and numerator have 5, we will cancel this thing out. Only 3 over 9 will be left, and 9 is 3 times 3. Therefore, 3 and this 3 will cancel out. And there's only 1 on the numerator, and the final answer will be 1 over 3. And this is the normal case. Now you may wonder, what's the not normal case? Well, it is the case with improper fraction. And where comes an improper fraction? Well, it actually comes from a mixed number. So whenever we have a mixed number, we need to first convert it into an improper fraction, and then we can do the simplification. Let's have a look at an example with a mixed number, 3 and 3 over 5. Now, in order to convert it into an improper fraction, we're going to do 3 multiplied by 5 plus the 3. So it's this 3 multiplied by this 5 time plus this 3 over here. 3 multiplied by 5 plus 3 over 5, and that is 15 plus 3 over 5. And we will get an 18 over 5. Now 18 over 5 cannot be cancelled out any further, so that's our final answer, and we are done. Okay, the next thing is multiplication of fractions. And multiplication of fractions is quite simple. Top and bottom, you multiply them, and then we will cancel down. So let's have a look at this example. 2 over 5 multiplied by 3 over 7 multiplied by 5 over 6. So 5 and 5 will cancel out here, so I'm going to circle this, and 3 and 6 is also going to cancel out, and 6 is 2 times 3, so we'll have 2 left here as the denominator. So we will get 2 in the numerator, and for the denominator we have 7 and 2. 7 and 2 multiplied together is 14. Simplify down, 2 over 4, 14 is 2 times 7, so we'll end up with 1 over 7. And that's done. But how about if we have a mixed number multiplied together? Well, when we have a mixed number, we will have to change it into an improper fraction first, just like we did for the simplification of fractions. Let's go to this example, 8 and 1 over 4 multiplied by 4 and 4 over 11. Both are mixed fractions, and we're going to turn them into an improper fraction. So 8 and 1 over 4 is 33 over 4, and 4 and 4 over 11 is 48 over 11. And then 33 and 11 is going to cancel down. 11 will become 1, and 33 will become 3. 4 and 48 will cancel down. 4 will become 1, and 48 divided by 4 is 12. And that will give us 3 multiplied by 12. That is 36. And we're done. That's our final answer because denominator is 0. Now we will look at division. And just like multiplication, if we have a mixed fraction, we're going to first turn it into an improper fraction and then do the division. But unlike multiplication, we just multiply top and top, bottom and bottom. For division, we're going to turn the fraction upside down and then multiply. So Let's have a look at this example. 3 and 1 over 9 divided by 14. If we were to solve this, first of all, we will see 14 as 14 over 1. So 3 and 1 over 9 will be changed into an improper fraction, and that will become 28 over 9. Then division sign will change into multiplication sign, followed by 1 over 14. Because we turned the fraction upside down to change the sign. And that will give us 28, and 14 will cancel out. 14 will become 1, 28 will become 2, and 2 multiplied by 1, 2 over 9 is our final answer. And that's done with division. The next thing we're looking at is addition and subtraction. So to add or subtract a fraction, what we do is put them over a common denominator if they are not already in a common denominator. Let's have a look at this example. 7 and 2 over 3 minus 1 and 1 over 6. Now for our convenience here, we will also turn them into an improper fraction. That will become 23 over 3 minus 7 over 6. And since they are not already in a common denominator, 3 and 6 are not, so we're going to make them to turn into both into 6. So that's 46 over 6 minus 7 over 6. So we can write it like this. Like this. Then we will get 39 over 6. And if we were to put our answer as a mixed number, it would be 6 and 3 over 6. And we have to simplify this 3 over 6. And we'll get 6 and 1 over 2. And that's done. Now here comes the order of operation. And we need this order so that everybody gets the same answer to a calculation. So we have a rule called Bitmas, and Bitmas is only here because it will help us to remember the order. Bitmas. The B stands for bracket, the I stands for indices, DM stands for division and multiplication, AS stands for addition and subtraction. And let's have a look at this example. Help us understand what Bitmas is. Let's say 125 divided by bracket 7 multiplied by 4 minus 23 squared divided by 5. Now the first thing we're going to do is brackets. And we have a bracket here, so we're going to first simplify the things inside the bracket. And to simplify the things inside bracket, we need to use Bitmas again, because we have here multiplication and subtraction. So we're going to do multiplication first before we do the subtraction. 7 multiplied by 4 give us 28. And 28 minus 23 will give us 5. So the whole thing over here is just 5. So then we have 5 squared, 125 divided by 5 squared divided by 5. Now we will move on to indices, which is this 5 squared. So simplify 5 squared into 25 divided by 5. We have this 125, we're going to copy it down. So we just have division right now. So we can do 125 divided by 25, and then we will get 5, and then 5 divided by 5 will just be 1. So the final answer is 1. Now we will look at significant figures and decimal places. So significant figures can be simplified to SF, and decimal places can be simplified to DP. The difference between SF and DP is that for SF, we will start counting from the left to the right, and we will start from the first non-zero digit in the number. Whereas for the decimal places, we will start from the decimal point and start from the first decimal. So let's look at an example with significant figures first. Let's say we have 761, and we were to write it correct to one significant figures. Then we will start from before this red line, and if the next number is greater than or equal to 5, we will round up. So if 6 is greater than 5 or equal to 5, we will round up. 6 is. So 7 will be round up into 800. And that's done. The first significant figure is always non-zero digit. And for both decimal places and significant figures, we will always count from the left to the right. So let's look at an example with 3 significant figures now. Let's have this example 0.5058. Then again, we're gonna draw a red line. Now we will not start from counting at 0. We will start from 5. So this is the first significant figure. This is the second. This is the third, and this is the fourth. Since we're taking 3 significant figures, we will start from here before this red line, and we'll look at the number 8 now, which is the number right after the red line, and 8 is greater than 5, so we are going to round up. Therefore, we'll get 0.506. 5 plus 1 is 6. So that's done with 3 significant figures. What if we have, now again, we will round this number into 3 significant figures. Now with a different number, 0.07035. Again, we will count the significant figures. This is the first one. This is the first that comes up, but for significant figures, we're going to start from this, which is the first non-zero. But here you will see a 0 after the 7. So this one will be the second significant figure. But you may ask, didn't we just say that we're going to first start with a non-zero digit? Well, if a 0 digit that follows after a first non-zero digit, it will still count as a significant figure. So this is the third one. This is the fourth one. We're not going to skip this 0 here. Okay. So we will put this into 3 significant figures. Therefore, we'll draw a line over here. Now, this 5, it is equal to 5, the number right after the red line. So are we going to round up or round down? Well, if the next number is greater than or equal to 5, we're going to round up. So in this case, we're rounding up. 3 plus 1 is 4. So our final answer would be, I'm going to use this color, 0.0704. And we're done with significant figures. Now we will move on to decimal places. Let's have an example to correct to 1 decimal place. 3.0524. If we were to put this correct to 1 decimal place, what we will do is again draw a red line, but now we will not count significant figures. We will start counting from the decimal point over here. Therefore, we're going to draw a line here. This is our first decimal place, 0. So the number that follows the red line is 5, so we're going to round up. Therefore, 0 plus 1 is 1. Our final answer would be 3.1. And the next thing coming up is our standard form. And the standard form will just look like a to the power times 10 to the power of b, where a is a number between 1 and 10. So it's a one-digit number, and it cannot be equal to 10, because 10 is a two-digit number. And b is an integer, and it can be positive or negative. The sign doesn't matter. So let's just go to an example to help us understand this better. It's not as hard as it sounds. So if we were to write this number 568 into a standard form, well, we first need to make sure that a is between 1 and 10, can be equal to 1, but never to 10. So it would be 5.68. Now you will think, multiply by 10 to the power of something. We need to write something here. So what shall we write as the indices for the power of 10? Well, we will think like, what shall I do to 5.68 so I can get the same answer to 568? Well, I need to multiply it by 100, right? And 100 is 10 to the power of 2, 10 squared. Therefore, the final answer is 5.68 multiplied by 10 to the power of 2. And if you were to check this, you would just do 5.68 multiplied by 100, and it is the same as 568. So this equation makes sense, and that's our final answer. Now let's look at one more example, in which it gets a little bit more complicated. Brackets 4.5 multiplied by 10 to the power of 4 times 6 multiplied by 10 to the power of 3. Now there's two ways to do this. One, as you might have already guessed, is just to do separately the two brackets. So the first thing that I'm going to do is 4.5 times 10 to the power of 4. And second thing I'm going to do is to break the second bracket and then multiply them together. But that will be too time consuming, and we do not have time for that if we don't have our calculator around. So what we're going to do, it's just 4.5 multiplied by 6 and 10 to the power of 4 multiplied by 10 to the power of 3. Therefore, 4.5 multiplied by 6 will give us 27 multiplied by 10 to the power of 7. And 27, we said that a should be between 1 and 10. Therefore, 27 is not between 1 and 10. We're going to make it into between 1 and 10. So it will become 2.7 multiplied by 10 to the power of something. But that's something we still need to find. Now, what we do to find that indice is, what are we going to do to 2.7? Or what are we going to do to 27 to get 2.7? Well, we divide it by 10. Yeah. Since we divided by an extra 10, in order to make up for this division, we're going to multiply it by an extra 10. So that means we will cancel this out. Therefore, 10 to the power of 7 multiplied by 10 will be 10 to the power of 7 plus 1. So 10 to the power of 8. So 2.7 multiplied by 10 to the power of 8 will be our final answer. If we were to check this, do 2.7 multiplied by 10 to the power of 8, and let's see if they equal to the previous two equations. And that's pretty much it with our standard form. Now what if our indices, our power of 10 is a negative one? Let's look at some example with that case. Let's say we have 0.0009. And we were to write this ordinary number into a standard form. We said a have to be between 1 and 10. Therefore, we'll take a 9. Yeah. Multiply by 10 to the power of something. Now we will think again what we're going to do to 0.0009 to get us a 9. Clearly, we're going to multiply it by, let's say, 10 to the power of what? So we will count. No, there's many decimal places here, so it gets a little bit more complicated. We're going to use our red pencil. 1, 2, 3, 4. Notice that we've moved 4 steps to the right in order to get 9, because 9.0 is 9, and our new decimal point will be here. Therefore, we've moved 1, 2, 3, 4 steps, so we're going to multiply it by 10 to the power of 4. But if we were to go from 0.0009 to 9 times 10 to the power of 4, we are actually moving to the right. But if we're moving from 9 to 0.0009, we're doing the opposite. Therefore, the opposite will be a negative number. 9 times 10 to the power of negative 4. And that's our final answer. And if we were to check this answer, if you are not sure whether it's correct, what we're going to do is to write a bunch of zeros in front of the 9, and we're going to shift decimal places. So originally, the decimal place for 9 is here, and then if we were to shift 4 places to the left, because it's negative, 1, 2, 3, 4, the new decimal place would be here. Yeah, it will be here. So if we were to write this number down, it's 0.00309. And you will notice that these two numbers, they equal. Therefore, our answer is correct. And we're done. Now, let's just quickly look at a standard form division without using our calculators. I have some empty space here. Bracket 2.4 times 10 to the power of negative 2 divided by 8 times 10 to the power of negative 1. Just bear with me for another few seconds, and we'll be done with standard form after this. This equals 2. Now there's still 2 ways to do this. One is to break the 2 brackets separately, and the other one is, like we talked about, multiplication. It's just 2.4 divided by 8 times 10 to the power of negative 2 divided by 10 to the power of negative 1. And now you may have already noticed that if we divide 10 to the power of negative 2 and 10 to the power of negative 1, we are subtracting the powers. So first, let's break 2.4 over 8. We will get 0.3 multiplied by 10. Now, negative 2 minus negative 1 is equal to negative 2 plus 1. And negative plus 1 is 1 minus 2. And that will give us negative 1. Now we need to make a between 1 and 10. And that should only be 3. But what shall we do to 3 so that it can equal to 0.3? Well, we're going to multiply it by 10 to the power of negative 1, right? Because 3 divided by 10 will be 0.3. And then we still need to move this 10 to the power of negative 1 down. Don't forget that. Times 10 to the power of negative 1. So we will get 3 multiplied by 10 to the power of negative 1. Since it's multiplication, we are going to add these two, plus negative 1. Therefore, we'll get 3 times 10 to the power of negative 2. And that's our final answer, and that's done. Moving on, the next chapter is percentages, and this is another easy chapter. If you were to find something as the percentage of something else, what we basically do is to put the first number over the second number and then multiply it by 100. Let's look at an example to help us understand this concept. If we were to calculate $10 as a percentage of, let's say $90, what we're going to do is do 10 over 90. Then we're going to multiply by 100, so we get a percentage. So 10 over 90 is 1 over 9. 1 over 9 multiplied by 100. You can enter that into your calculator. You will get around 11.11%, near to the 2 decimal places. Correct, to 2 decimal places. Now, let's look at another example in which we are given the percentage and the original number. We want to find how many percent of something. Let's say if we were to calculate 5% of $80. What we're going to do is, first of all, convert 5% into a decimal. 5% is just 0.05. If you don't know how to convert this, what you basically do is 5 divided by 100. Because percentage, we're working with the 100, 10 to the power of 2. So, after we found the decimal, we will multiply this by 80. This is much easier. Yeah, if we do that, we will get us a $4. So 5% of $80 is just $4. And we're done. So whenever we see the word off, because we're finding 5% of $80, we will do multiplication. You need to quickly relate these two whenever you have this in your question. The next thing we have is percentage change, and I'm just going to quickly tell you a little formula that I use to calculate percentage change. It's the new minus the old over the old. You can also call the old as the original, and multiplied by 100. And then new minus the old is just the value of change, right? Try not to write this thing out in exam because it's just for you to understand it better. And this formula will help you to find percentage change. And there are 2 types of percentage change. One is percentage change increase, and the other one is percentage decrease. Now, if we were to find percentage increase, the percentage change will always be positive. And similarly, we do the opposite for decrease, and percentage change for something decreasing, it will be a negative percentage change. Therefore, let's look at one example to help us understand this concept better. If somebody's running time decreases from 32 seconds, this is the old time, to just 24 seconds, work out the percentage decrease. So percentage decrease can be calculated by the formula that we wrote down previously. So we would do the new minus the old, and the new one is 24, minus the old is 32, over the old. The old is 32. Yeah, and then we will multiply by 100. Multiplying by 100 is quite easy to understand. Why are we multiplying by 100? Because we want to get a percentage. So this will give us 8 over 32, which is 1 over 4 multiplied by 100 equals to 1 over 4 multiplied by 100, and that is 25%. And since these are all negative 25% will also be negative. If we were to work out the percentage decrease, since the question asks us to find percentage decrease, we don't need to write this negative sign over here because it's already a decrease. If the question asks us to find percentage increase instead of a decrease, then we can put the negative sign. So no need to put negative sign here. And we're done. Moving on, we have percentage increase or decrease. Before we go and look at any examples, I want to introduce you to a concept called multiplying factor over here in this table. Now, if we have a percentage increase of 25%, if we were to find the multiplying factor of an increase of 25%, we first of all going to find 25% as a decimal, and that is 0.25. And then we're going to add it to 1. And it will give us 1.25. What if we have a 25% decrease? Well, it's pretty similar, but instead of addition, we're going to do subtraction from 1. 1 minus 0.25. The reason that we do subtraction and addition to 1 is actually very simple to understand, because in the percentage increase, you can think like we're taking the original thing and we're adding another quarter to it. So we add the original number to 1, because you see 1 as the original whole of the thing that you are multiplying it by, that you're changing it. And in the case of percentage decrease, we're just taking a quarter away from what you originally get, so we subtract it from 1. So with that concept in mind, let's have a look at an example. A look at an example. Let's say we have $2,500 and you were to increase that by 10%. Increase that by 10%. What will the new price be if we increase that by 10%? Well, we said increase something by a percentage, we're going to add it to 1. First conversion decimal and then add it to 1. So 0.1 plus 1 will give us 1.1. So the multiplying factor we already found, it's 1.1. And we're going to multiply that by 2,500 in this case. 1.1 multiplied by 2,500, and we will end up with 2,750. You can find that with your calculator. What if we were to decrease the same number, still 2,500, decrease by 99%? Well, if it's decrease, we're first going to find the multiplying factor and we're going to subtract it from 1. So 1 minus 0.99 would be 0.01. And then we're going to multiply 0.01 multiplied by 2,500. Again, we're going to use our calculator, and the final answer we'll get is $25. And that's it with this example. The next thing coming up are prime factors, and from its name, you may have already guessed what it is. It's factors that are prime. As easy as that. And in order to find all prime factors of a number, we're just going to repeatedly divide that number by prime numbers. So just whatever that came to your mind, that is a prime number and it divides into that number, we write it down. And let's use an example to understand this better. Let's say we have the number 72 and we were to find all prime factors of it. The only way to do that is we need to first think of a prime number. So that divides into 72. Well, 2 would be a really obvious one. So 72 divided by 2, and then we write that number over here. So that is 36. And then continue doing that with 36. An obvious prime factor of 36 is 2 again. And 36 divided by 2 gives us 18. And one more time, an obvious prime factor of 18 is 2 again. 2 times 9 is 18. So notice that the two branches below that number will multiply to give the number on top of them. So then we go and do 9. 2 doesn't go to 9, so another prime factor would be 3. 3 is also a prime. So 3 times 3 is 9. And we're done. The last number over here must be a prime as well, and 3 is a prime. So notice that all the branch on the left hand side, they are all prime. 2 is prime, 3 is also prime. So we're going to write it all together. 2 times 2 times 2 times 3 times 3. Now this looks a bit long and more complicated. We must write it in index form, that is putting all the 2's together and 3's together. So 3 2's multiplied together will give us 2 to the power 3 times 2 3's multiplied together will be 3 squared. And our final answer should always be in index form. And that's pretty much it with prime factors. Next, we have highest common factor and lowest common multiple. Just like its name, it's the same thing as its name. Highest common factor is the largest common factor to a set of numbers. So it's numbers that would divide into those set of numbers, and lowest common multiple is the smallest common multiple to a set of numbers. So it's a number that those sets of numbers can divide into. So it's usually bigger or equal to those sets of numbers. Whereas highest common factor is usually smallest. It's usually smaller than those sets of numbers, or it could be equal in some severe cases. So it's easy to remember this because when it says highest common factor, that means it cannot get as high, so it will be smaller or equal to those numbers. Whereas lowest common multiple means we're trying to get the smallest number. We're trying to get the minimum. Therefore, it cannot get as low. Therefore, it's equal or bigger than those sets of numbers. With that being said, we will look at a couple of examples. Let's say if we were to find the highest common factor of two very simple numbers to start with, of 6 and 8. We want to find the highest common factor of 6 and 8. What we're going to do first is to apply the knowledge that we learned how to find the prime factors of 6, and then we're going to find 8, and then we're going to combine them together. So to find prime factors of 6, we're going to list this 3 branches, 2 times 3. So that's done for 6. And for A, we have 2 times 4, and 4 can be simplified to 2 times 2. So 6 equals to 2 times 3, and 8 is 2 to the power of 3. And then, since we're trying to find the highest common factor, and we said that highest common factor cannot get as high, therefore it should be smaller than 6 and 8, or equal, which I don't think will be equal in this case. It cannot get as high, therefore, from this thing over here, we're going to work out the answer. we must find such number that both 6 and 8 have. That means 2. Both of them has a 2 to the power of 1. Therefore, the highest common factor of 6 and 8 is just 2. And that's done. If we were now to find with the same number 6 and 8, but this time we want to find the lowest common multiple. Well, what do we do now? Actually, we still use this box over here. Now this looks like some kind of a TV. Okay. But lowest common multiple cannot get us low. Therefore, we need to find a number that includes both 2 times 3 and 2 to the power 3. Therefore, it should include a 2 there, and it should include a 3 there. But how about 2 to the power of 3? It should also be there. So what we're going to just write is 2 to the power of 3 times 3. Yeah, we don't need to write that 2 there. Over here, we don't write it anymore because 2 to the power of 3 is actually a multiple of 2. So that's done. That's our final answer for lowest common multiple. And realize that highest common factor 2 is smaller than 6 and 8, and lowest common multiple 2 to the power 3 times 3, which is obviously bigger than 6 and 8. But for our final answer for lowest common multiple, it will be good if we can leave it as an ordinary number. So 2 times 3 multiplied by 3 is 24. And that's it. Ratio is our next topic. You can see ratio as a way to compare quantities, and then we're going to divide the ratio that we're given into the number that there are in total, and then we can allocate these to different things. Let's have a look at an example. If we were to divide 120 pounds into the ratio 1 to 2 to 5. Well, you can understand this as being divided into 3 different people. So the first person will get 1 portion, the second person will get 2 portions, and the third person will get 5 portions. So that means 1 plus 2 plus 5 would give us 8 portions in total. Yep. Therefore, we want to divide this 120 pounds into 8 different portions so we can know how much each person will get. Therefore, we do 120 divided by 8, and that gives us a 15. So the first person will get 1 portion. So the first person will get 15. The second person will get 2 portions. So 2 times 15 will give us 30. And then the third person will get 5 portions. So we will do 5 multiplied by 15, and that's a 75. So this is our final answer, 15 to 30 to 75, when we divide 120 into this ratio. The next topic that we're looking at are compound percentages. And compound percentages are mainly used when we go to save our money in a bank and we want to find the compound interest after a few years, and we want to know how much we will get after that. So before we go and do any examples, we're gonna first get our head around this table over here. Let's go with an example. Let's say if we have an annual appreciation, so annual increase of 15% in a period of 2 years. So our multiplying factor would be, if we don't have that n years, we would get a 1.15 multiplying factor, because when we convert 15% to a decimal, it is 0.15, and then we add it to the number 1. So we will end up with 1.15. The reason that we added to 1 is because we want to get the original value, and then we're gonna add an extra 15% on the original value. And that's the reason why. And if we were to depreciate by 15% for 2 years again, then the multiplying factor would be 0.85. But notice that if we just write our answers like this, we're not using the number of years which we are supposed to do so, because in 1 year time we're gonna decrease it by 0.85, but in 2 years time it will be multiplied by 0.85 multiplied by 0.85. So we're just going to shorten that into 0.85 squared, and that applies the same for 1.15. So the multiplying factor will have a power of the number of years that the money is safe in that bank account, for example. So from this, we will deduce a formula which you don't need to memorize because you have already understood if you have understood this table over here. So that formula is when we increase a quantity by R% for n years, we will get a formula of 1 plus r over 100 to the power of n, just like we've talked about. We're adding 1 to it, and r is over 100. The reason behind that is because we are working with percentages, and percentages, it is always over 100. And if we were to decrease r by r% still for n years, nothing changes except from the sign. It will be 1 minus r over 100. Still, brackets to the power of n. And the reason behind that is because we're taking the original value, and then we're, in this case with the table, we're taking another 15% off from what we get. So we're subtracting it from 1. And that's it with compound percentages. Now we are ready to look at some example. Here we go. If I were to invest, let's say $2,000 into my bank account at a compound interest of 5% per year, and how much will I have after 2 years' time? 2 years' time. Well, in order to calculate that, we know that n years, n equals to 2. So we can substitute everything into the formula that we just derived. So 1 plus r over 100 to the power of n. So r would be 5. So I would just do 5 over 100 plus 1. And n years is 2. So to the power of 2. 5 over 100, if you've realized, is 0.05, and that is exactly the same if you just convert 5% into a decimal. So 1 plus 0.05, it's 1.05 and squared. And then we're going to multiply this by 2,000. Multiply that by 2,000. I'm going to write it here. 2,000 multiplied by 1.05 squared, and then I will end up with an answer 2,205. And the unit is dollars. And that's it with this question. Next thing we have inverse percentages, and unlike any percentage topics that we've looked at, this time we're working backwards. That is, we're given the final value and the percentage increase or decrease, and we want to find the original value. So let's have a look at this example. In my math test, my test score mean was X%. It is now 78.2% after an increase of 15% and a decrease of 15%. Find X. Now pause this video and have a go. I'm now assuming that all of you guys have had a go on this question. Hopefully no one got an answer of 78.2%, right? It's a really common mistake because when someone look at this question, they say, oh, increase of 15%, decrease of 15%, that's going to cancel out. So it's still going to be that original value. And that is wrong because when you consider with multiplying factor, when there's an increase of 15%, the multiplying factor would be 0.15. And when there's a decrease of 15%, 1 minus 0.15, we will get 0.85. Let x be the original value multiplied by 1.15 and then multiplied by 0.85. And then we will get 78.2. 78.2. In order to find x, we're working backwards, so we're going to divide both sides by 1.15 multiplied by 0.85. And we will end up with an answer x equals to 80%. And that's it. Our final answer is 80%. The next chapter is lower bounds and upper bounds. And lower bounds and upper bounds are basically just maximum and minimum values with a range. And in order to find upper bounds, we just add half a unit to the original value, and to find the lower bound, we just subtract half a unit from the original value. Let's understand this with an example. Let's say we have the number 17 and we want to find the upper bound and lower bound to the nearest unit. So we will imagine the unit as being just the number 1, and we want to find upper bound first before we go to the lower bound. We would do 1 divided by 2, so that's half, 0.5. We would add that to 17, the original value, and that would be our upper bound, which is 17.5. And for the lower bound, you can either just do 17 minus 0.5, or you could do the upper bound minus 1, yeah, whichever you prefer. So let's look at one more example. Now with decimal places, if I were to write the number 2.5 to the nearest 0.5, then again I'm going to divide this 0.5 by 2, and that will give me a 0.25. And then I would add and subtract that from 2.5, so the upper bound would be 2.75. We added, and for the lower bound it would be 2.25. Very easy. Moving on, we will look at direct proportion and inverse proportion. Now, these two proportions are represented by these two graphs. The graph on the left is the one with direct proportion, and on the left is the one with inverse proportion. To recognize a direct proportion, you will always see a graph with a straight line through the origin. So when the graph one is multiplied or divided by a number, the other y will also be divided or multiplied by that number. And the ratios stay the same as they increase or decrease. So the equation for a graph with direct proportion will be y equals to kx. Whereas for the inverse proportion, the graph relationship is a reciprocal graph, and one quantity increases at the same rate as the other quantity decreases. Now this is really easy to understand because if you take a point here, and you will see that x is very low, whereas y has a very high value. So when x is low, y is high, and when x at this point is high, y is low. So that makes up for it. Therefore, the equation for the inverse proportion would be y equals to k over x. So the product is constant because if you move this x to the left-hand side, so you multiply both sides of this equation by x, you get yx equals to k. So y multiplied by x gives us a constant number. So the product is constant. And that's it. Fractional indices are the next topic that we're going to look at. Fractional indices are very easy once you know this rule here. X to the power of n over m equals to square root m to the power of n brackets. And that can also be simplified into just the power inside the square root. Notice that this m should be the small one inside the root. So once you know this, combining the laws of indices that we knew from before, solving questions relating to fractional indices are really easy. So let's go on to look at a few examples. 9 to the power of 3 over 2. I want to work that out. Then I will separate this into 9 to the power of a half multiplied by 9 to the power of 2 over 2, so that is 1. And the reason that you can separate it like this is because when you add 1 over 2 and 2 over 2, you will get 3 over 2, and that's the law of indices. When we multiply, we just do addition. Therefore, we will simplify that further. 9 to the power of 1 over 2 basically means n equals to 1, m equals to 2. Therefore, when m equals to 2, we have a square root, and x is 9. So 9 to the power of a half is square root of 9. Yeah, does everybody get that? Because there's a 2 here, which we don't need to write. Therefore, 9 to the power of 2 over 2 is just 9 to the power of 1. So we don't need to write that 1. Square root of 9, that's easy. It's 3 multiplied by 9, copied down. And 3 multiplied by 9 is 27. And that's our final answer. Next thing we're looking at are negative indices. Once we know negative indices, we can combine that with fractional indices and solve much more questions. Let's have a look. Negative indices are very easy as well. All you need to know is this rule here. X to the power of negative n equals to 1 over x to the power of n. And once you know that, you can deduce much more formulas by yourself. So let's now let the base be x over y instead of just x, that to the power of negative n. Well, we can just substitute in whenever we have x to be x over y. So that will be 1 over x over y to the power of n. And that will be 1 divided by x over y to the power of n. So when we have division, it is basically taking the reciprocal of x over y, so it's equals to 1 times. So I'm going to write that times as a dot, just not to confuse with the x. Y over x to the power of n. Therefore, 1 times anything, I can ignore that 1, so I'm going to rub this out. So we just get y over x to the power of n, original one. So the second one you do not need to memorize once you know the first one. And that's it. And once we know all that, we can look at much more difficult examples. 2 over 3 bracket to the power of x equals to 9 over 4. We can't work out the value of x straight away, but we can after we simplify 9 over 4 and break the brackets. So let's first break the bracket. 2 to the power of x over 3 to the power of x. Yeah, and 9 is 3 squared. So I'm going to write it 3 squared, and 2 is 2 squared. Sorry, 2 squared. You will notice a relationship. Well, there's a 2 here, and there's a 2 here, and there's a 3 here, and a 3 there. So we gotta somehow relate them. If we flip this fraction around, it's gonna look much more similar, and x should be 2. Therefore, we're gonna flip it around. And in order to do that, we must let x be a negative number. Therefore, x equals to not 2, but negative 2. Moving on, let's look at one more example, and we're good to go. Let's say 8 to the power of negative 8 over 3 equals to 1/4 to the power of x. Now, we have a fraction on the right, and we have the number 8 on the left. We still need to find a way to relate these two. You'll notice that they're both divisible by 2. So how about I go and write them with the same base, 2. Well, I can actually do that. Yep. 1 over 4 is just 2 to the power of negative 2. And 8 is 2 times 2 times 2, so that's 2 to the power of 3. But I can't just throw away their powers, so I'm going to put in brackets and write down their powers. And 4 to the power of negative 2 as well. Then I'm going to go and simplify that further. Well, because we have a bracket, and then we're going to multiply these two straight away. So 3 multiplied by negative 8 over 3, the 3 is going to cancel out. Therefore, we're just going to have 2 to the power of negative 8 equals to 2 to the power of negative 2x. So x, it's easy right now, yeah? We've got an equation. Let me just write the full equation down without. Negative 8 equals to negative 2x. So x should be 4. And that's it. Putting decimals into a fraction is quite simple, but how about if the decimal will repeat non-stop? How can we turn a recurring decimal into a fraction? That's what we're going to focus on right now. In order to turn a recurring decimal to a fraction, we have to first find two numbers that is usually multiples of 10. So 10, 100, 1000. That's the usual cases. And what's common about these two numbers is that after the decimal point, the decimals are exactly the same. So let's understand this with an example. Let's say we have 0.93 recurring with two dots on 9 and 3. So this means it's going to go like 0.939393 and so on. So we're going to let 0.93 recurring to equal to x. So I'm going to write x equals to this. And then I'm going to find another number that also have something 0.939393 repeating. So that will be 93.9393 repeating. And 93.93 repeating, that would be 100 multiplied by this number. So 100 multiplied by that number is 100x. Now we know 100x equals to this, and x equals to that. What if I do 100x minus x? Then I will end up with 99x. And this 99x would equal to 93.93 repeating minus 0.93 repeating. And since after the decimal point, the two numbers, they equal, so what I will get left is just 93. Yeah, now I know 99x equals to 93. Finding x is so simple. So I'm going to write it for the next line, on the next line. 99x equals to 93, x equals to 93 over 99. Yeah, after I simplify that, divide both top bottom by 3, I will get 31 over 3. And that's done. I have successfully converted the recurring decimal 0.93 repeating into a fraction, 31 over 33. Now let's look at a slightly more difficult example. If I want to turn this decimal 8.029 with the 2 and 9 repeating. 2 and 9 repeating. What shall I do now? Now I still need to find two numbers whose number after the decimal point are exactly the same, just like this example here. They have 93 the same. So I need to first let this be x. And then I'm going to find 10x, that is 80.29 repeating. That is 10x. Now I will realize that x and 10x this time, they do not have the same number after the decimal point. Yep, here's the decimal point and here is the decimal point for the second number. And after the decimal point for the first number, I have 029. And after the decimal point for the second number, I have 29. So they aren't the same. So I need to find another number that is the same as 10x. That's much easier. So that would be 8,029.29. And 8,029.29 repeating, it's the original number x, this number, multiplied by 1000x. Yeah. Now, these two have the same number after the decimal point. So I can do 1000x minus 10x, and that gives me 990x. And if I go and subtract these two numbers, 80.29 repeating and 8029 repeating, 949. Okay, now I want to find x. So I will do this number, 7,949 divided by 990, and x would be 7,949 over 990. We cannot simplify that further, so that's our final answer. And that's it with recurring decimals. The next very important topic is conversion between areas. Now you may have already looked at conversions between units of length, that is kilometers into meters, sometimes meters into millimeters, conversions between lengths. But when we work with conversion between units of areas, we usually need to do everything doubled. That's a tip that I would usually tell myself when converting between areas. So let's look at an example. Let's say first we will say 1 meters converted into centimeters. That's a conversion between lengths. Then 1 meters equals to 100 centimeters. But if I change this into conversion between units of area, it will be 1 meter squared equals to how many centimeters squared? Well, we said that we're going to do everything doubled, so I'm going to do everything twice. So from 1 meters to go to centimeter, I will multiply by 100, and if I repeat this process twice, I will get 100 multiplied by 100. So that will give me 10,000 centimeters squared. So whenever we're working with units of area, we would do double the things that we would do to a normal conversion between the units of length. Let's look at a real example, and I'm going to prove that to you guys. Let's assume we have a rectangle of length 2 meters and height 1 meter, and I want to find the area in millimeters squared. How am I going to be able to do that? Well, the most easiest way is to find the area first of all in meters squared and then convert this into millimeters squared. So let's do that. In meters squared, it would be 2 times 1, so it's 2 meters squared. I want to find the relationship between meters and millimeters. So let's first find the relationship between units of length. So 1 meter equals to how many millimeters? Well, 1 meter equals to 100 centimeter, and 1 centimeter equals to 10 millimeters. So I'm going to add another 0 millimeters. So we're going to repeat that process twice. If we were to convert the length, we would do multiplication of 1000 and repeat that process twice. So I'm going to multiply 2 multiplied by 1000 squared. So 2 1000 multiplied by together. And that will give me this number. Yeah, with 6 zeros following the number 2, and the new unit will become millimeters squared. Now to prove this, we can try and convert the lengths before we go and find the area. So I'm going to convert 2 meters straight away into millimeters. So I'm going to write it over here into millimeters. That will be 2 times 1000, so 2000 millimeters. And 1 meters into millimeters, that will become 1000 millimeters. So if I were to multiply those two numbers, let me get a different color. So let's try this. 1000 multiplied by 2000. And both of them are in millimeters, so my unit would be millimeters squared. And 1 times 2 with 6 zeros and following. And that's it. You will realize that this answer is the same as the answer we found before. So my method worked. Now, similarly, we will look at converting between units of volume. Just like we did for conversion between units of area, we're just going to do everything 3 times instead of 2 for the area. Yeah, and that makes sense because a volume of a shape is usually something cubed, right? Centimeters cubed or meters cubed, something like that, to find the volume of a shape. So we're going to do this example. Let's assume that this is a cube of sides 100 centimeters each. So the length of all these are 100 centimeters, and then we want to find the volume of this shape in meters cubed. Well, first of all, we need to find the volume of this shape in centimeters cubed because the lengths are given in centimeters. So, and then we're going to convert this centimeters cubed into meters cubed. It would be 100 to the power of 3. Yeah, centimeters cubed because 3 sides multiplied together and all 3 sides are 100 centimeters. So it will be 100. Will be written 3 times, and then that's centimeters cubed. Now to convert this into meters cubed, we are going to first find the relationship between meters and centimeters, relationship between its length. So I would say 1 meter equals to 100 centimeters. So we will do that 3 times. So I'm going to move 1, 2, 3, 4, 5, 6. Therefore, now I know that this thing all here equals to 1 meters cubed. Now we can use this example to give us a conclusion. We will convert this into powers of 10, so that's 10 to the power of 6 centimeters cubed. And that equals to 1 meters cubed, so we know 1 meters cubed equals to 10 to the power of 6 centimeters cubed. We know that the relationship is 1 multiplied by 10 to the power of 6 to convert from meters cubed into centimeters cubed. But before, the converting between lengths was just 100. Therefore, 100 is 10 to the power of 2. Now, 10 to the power of 2 became 10 to the power of 6. It means that we repeated the multiplication of 10 to the power of 2 3 times. So that's our relationship with working with units of volume. Now we will move on to compound measures. Well, there are 3 basic compound measures that we're going to look at in GCSE. And they are speed equals to distance. Speed equals to distance over time. And density equals to mass over volume. And lastly, we have pressure. Pressure is quite easy to understand, is force over area. The reason that is over area is because we want to know that when a force is applied to something, we want to know how big that area is so they can share the force between them. Therefore, we divide it by area. And another way to remember these three rules, as I call them rules, is by their units. Therefore, the usual unit for measuring speed is meter per second, or sometimes it can be kilometers per hour, depending on the question. Write a comma here. And for density, it's usually grams over centimeters cubed, or it can also be, let me write that through again. Yeah, or it can also be kilograms per meters cubed. And for pressure, it's newtons per centimeters squared, or newtons per meter squared. So the reason that I said there's another way to remember these three rules by using these units is because whenever, let's say when you want to find the speed for the first rule, whenever you see a number with a unit meter and another number with a unit second, it means that you automatically know the value for the distance, because distance is measured in meters or kilometers, in this case meters, and time now in this case is measured in seconds, so you would do meters multiplied by that second number. So let's have a look at another example. Let's say in a question you're given a number in Newton and another number in meter squared. So you would divide those two because you know pressure is newtons over meter squared. Therefore, your final answer would be pressure. Yeah, and similar for density. If you know a number in kilograms and another number in meters cubed, you will automatically know the density because you just do a division between these two numbers. And similarly, if you are given, let's say now, we're still working with density. If you are now given a number in grams and its density, so its density is usually given in how many grams per centimeters cubed in this case, you can find centimeters cubed, can't you? Because if you know two values, let's say you know density and mass, you can find volume, because volume now, if you move volume to the left-hand side by multiplying both sides by the volume, you will know that volume equals to mass over density. Yeah. So these three equations will give us many more. Let's say the first one, speed equals to distance over time. You can also make time the subject. That would be time equals distance over speed. Yeah. These ones can be converted to many more rules, but we just need to know these three. That will be enough. Let's have a look at an example of a cuboid. Now, this is a cuboid. I'm going to try and draw the other side as well. Okay, and this side is 23 centimeters. This side is 10 centimeters. I'm going to label it here. And this side is 12 centimeters. All right, and the mass of this plastic cuboid, I'm going to write the mass, equals to 2,208 grams. I want to find the density of this cuboid in grams per centimeters cubed. Well, in order to do that, we need to refer back to the rules that we looked at. We knew that density equals to mass over volume, and we're trying to find either this or this, right? So let's go and find it. We already found a number in grams, which is 2,208. So for sure we're going to use that. And we need to find another number in centimeters cubed. Now the question haven't made it so easy for us, so we can just do the division. We need to now find a number in centimeters cubed by ourselves. So that would be the volume of this cuboid. If I multiply these three numbers together, 23 multiplied by 10 multiplied by 12, that would give me a number in centimeters cubed. So I'm going to enter that to my calculator, and I will end up with number 2,760 centimeters cubed. Well, now I know the number in grams and the number in centimeters cubed. I just do division right now to find the density. Well, 2,208 grams divided by 2,760. Again, I will use my calculator to find this. And I will end up with 0.8. And don't forget to write the units, grams per centimeters cubed. And that's my final answer. That's the density for this cuboid. Moving on, we'll look at a slightly different question. We will now work with pressure. Newtons and meters cubed, yeah, with area and newtons. Alright, area and force. So the question is, a force of 54 newtons is applied to an area of 21,600 centimeters squared. Work out the pressure, and we want to work out the pressure in newtons per meter squared. Well, this is actually easy because everything is given. We know the newton, we just need to find centimeters cubed. Oops, I made a mistake. Here is centimeters squared. We just need to find centimeters squared in meters squared. Therefore, we are going to use the knowledge that we had. We looked at that before. That's converting between units of area. So 1 meters equals to 100 centimeters. So 1 meter squared would be the multiplication of 100 twice. Therefore, it will be 10,000 centimeters squared. Well, in order to convert 21,600 centimeters squared into meters squared, we're just going to use this ratio of 1 to 10,000. Yeah, that's the ratio we found over here. To something to 21,600. So we need to find this number. Let's get this number to be x. So now, in order to find x, we're just going to do some division and multiplication. What we're going to do right now is to use the ratio 21,600. And I'm going to divide that by 10,000. Right? And I'm going to multiply that by 1. So it makes no difference. X, that will give me the value of x. Therefore, I'm going to use my calculator again. Divided by 10,000. Right. And then I will get x to be 2.16. And now that's converted into meters squared. Therefore, we know that now meter squared equals to, I'm going to write it here, meter squared equals to I'm going to not write it in this form. I'm going to write it like this, equals to 2.16 meters squared. Like that. We know newtons, it's given in our question, and we found meters squared. 2.16. The pressure is 54 divided by 2.16. So I would do that 2.16 and I will get 25 as my pressure. So the final answer is 25. Don't forget the units, newtons per meter squared. And that's it. Now, the next topic we're going to look at is a really important one, but not as though important in the exam sense, but for real life as well. Let's say if you go to a shop and you want to get a new iPhone. Well, if you can buy an iPhone 4 and an iPhone 12 for the same price, you would automatically go for that iPhone 12 because that is a better value for the same amount of money. But that is easy and obvious to see which one have a better value for the same amount of money. But what if it's not so obvious? Well, that's where math comes, and it will help us to decide which one is the better value for us. Let's look at an example now with, let's see, with pineapples, right? Tin A with pineapples, tin A has 450 grams of pineapples, and if I want to buy tin A, I have to pay $2.7, right? If I want to buy tin B contains 240 grams of pineapples, and I have to pay $1.36. Well, I want to decide which one to buy that gives me a better value for the same amount of money. But this is harder to visualize than the iPhone example. So what I'm going to do right now is to make their price the same so I can compare which one have more grams of pineapples, and I'm going to get the one with more pineapples. So I'm going to do both 450 and 240 divided by the value. So that's the dollars. So I'm going to do 14A 450 divided by 2.7. In this way, I can get how much grams of pineapples I can consume when I pay $1 if I do that division. So 450 divided by 2.7 will give me 166.6666. So I'm going to write 166.7 to the nearest decimal place. And then I'm going to do the same thing for tin B. For tin B, I'm going to do 240 grams divided by 1.36. That would be 240 divided by 1.36 is 176.5 to the nearest decimal place. Now it's much easier because all we have to do is to compare these two numbers. And these two numbers are in grams and are the amount of pineapples we can get for $1. Yeah. So obviously now 176.5 is much bigger. Rewrite this 0.5. It's much bigger than 166.7. Therefore, the tin B contains much more pineapples for $1 than compared to tin A for $1, but not for 1.36 and 2.7 because their price is different. So you would expect for different price to get different grams, but you would want to get the most amount of pineapples for the same amount of price. Therefore, tin B have a better value. Our answer would be B. Let's look at one more example. Now we're gonna look at perfumes, right? a small perfume, right? Small perfume would be 80 millimeters for $100. A medium perfume would be 160 millimeters for $180. And a large would be 250 millimeters for $280. I want to find which perfume will give me the best value. Again, I will do the division, right? Because that division method applies to every kind of questions when you want to find which product or service have the best value. But there is also another way, which I'm going to show right now. You will realize that when you multiply 80 millimeters here by 2, you will get 160 millimeters. Right? So that there's a relationship. First of all, we can decide whether the small or the medium have a better value. And then the one that has a better value, I'm going to compare that with the large, right? So 100 multiplied by 2 will give me 200. Therefore, if we charge the medium perfume at the same price as we charge for the small perfume, we would expect to pay $200, but the price of the medium perfume is only $180. Therefore, we know that the medium is of much better value than the small. So we're going to cross out the small. And then we're going to work with medium and large right now. This is hard because it's hard to find a relationship between 250 and 160 straight away by just looking at it, but we can use our calculator. We can do 250 divided by 160, and I will get a fraction that's 25/16, but we don't mind to be a fraction because we have our calculator, and then I'm going to multiply this number by 180. Now, if this result that we get is bigger than 280, which is the price here, then it means that the large is of the best value. But if the number that we get from this multiplication is smaller than 280, it means that medium is the one of best value. And the final result for this multiplication is 281.25. Therefore, this one is just by $1.25 bigger than 280. So we said if it's larger than that number, the large will be of the best value. And our final answer is that the large perfume is of best value out of all these three. And that brings us to the end of comparative costs. What follows next are taxation. And first of all, we'll look at sales tax. Sales tax. And to work with those, we have to work with proportions. That's like percentages or fractions and multiplying factors. Let's have a look at this example. Let's say this computer costs $1,200 and plus a sales tax of 15%. We want to calculate the selling price. This means from what's given in the question, the sales tax is not included in this 1,200, and a selling price is the price that consumers usually buy the computer for. So selling price is the original price plus the tax, plus the sales tax. So the original price we already know from the question, but what's the sales tax? We know only that is 15%, but what's 15%? Well, we are first going to convert this 15% into a decimal. So that's our multiplying factor. It's 0.15. Alright, so we're going to do 0.15 multiplied by 1,200, and that will give us $180. Right, and that's our tax. If we want to find the selling price, we know it's the original price, which is 1,200, plus the tax, and the tax now we already found it's 180. So when we do this addition, we'll get 1,300. Sorry, 1,380. Right, that's it. That's our selling price. But another way to do this is not to find 0.15%, but instead to go for 1.15%. Let me use a different color. 1.15%. And that's our multiplying factor. And we looked at those before at the start of this video, multiplied by 1,200. Now, with this 1.15, we do not need to do any further calculations. If we do 1.15 multiplied by 1,200, we will end up straight with 1,380. Yeah, we do not need to do any further steps. So this method here, the green one, is much simpler than the yellow one. So you can decide which one is better to use. Okay, now moving on. Let's look at one more example. Let's say now we will work with, let's say this. Okay, if I buy a computer game for $36, including, now you need to pay extra attention to this word including, a sales tax of 20%. Calculate the sales tax. Sales tax. We do not know the sales tax by just looking at the question, so we need to do some calculations. $36 is the price that consumers are going to buy the computer game. So that included the sales tax inside it. So $36 actually equals to 120% of the original price without the tax. Yeah, because it's 100% of the original price is the price that tax is not included. So 100 plus 20%, it's the $36. So in order to find the 100%, which is the original price, it's actually easy to do because you can first convert 120 into a decimal, 1.2. And then you can say, well, 100% is 1 and 120% is 1.2. In order to find 1, we can just divide 36 by 1.2. So I'm going to do that. 36 divided by 1.2. And I will end up with 30. So I now know that the original price without the tax is 30, and when we include a tax, it is 36. So I do a subtraction. The tax is just $6. And that's my final answer. Sales tax equals to $6. And that's it with this type of questions. Now let's look at a slightly more challenging one. Let's say, now I will buy something at $Y, including a sales tax of 15%. Now, I want to show that the sales tax I pay would be 3y over $23. Well, this is the type of question we need to prove. So it means we need to show every one of our steps. We need to write it down, the steps, clearly, in order to get a full mark. So the y dollars includes the tax of 15%. So y, it's 150%. Sorry, 115% of the original price without the tax. Yeah, so what I'm gonna do is the same as we did for the previous question, to convert 115% into a decimal, so it will become 1.15 as a decimal. Now, if I want to find 100% of the original price by using y, what I'm gonna do is just like what we did for our last question. We did division, so I'm going to do the same here. Let's go back here. We're going to do y divided by 1.15. Now I'm going to leave it like that and then simplify in the end. Then y over 1.15 is just the original price, but we want to show that the tax is equal to this. So the tax is 15% as given. So if I multiply the original price by the tax, 15%, then I will get the exact amount of the tax, right? So that's what I'm going to do right now. I'm going to say I will do y of 1.15, the original price, multiplied by the tax, 15%. So now I'm going to do y over 1.15. I'm going to show every one of my steps. And then 15% converted into a decimal is 0.15. So that is 0.15 over 1.15 multiplied by y, right? And that can be simplified further. 0.15 over 1.15 gives us 3 over 23. If you enter down to a calculator, it will simplify it for you. So 3 over 23 y can be also placed on the numerator freely like that. And that's done for this question. Well, if you don't have your calculator, you can still simplify this fraction, which I'm just going to quickly show over here. Just in case if you're not allowed a calculator in your test. So 0.15 over 1.15. If you multiply top bottom by 100, you will get 15 over 115. If you divide both numerator denominator by 5, you get 3. 3 multiplied by 5 is 15, and 23 multiplied by 5 is 115. So that's how you do it without a calculator. And that brings us to the end of sales tax. This is as hard as any IGCSE questions can get for sales tax. The next topic, we will work with currency, and this is a topic that you guys are really familiar with, especially if you travel a lot. Whenever you go to a foreign country, you need to exchange your own currency into theirs, and we would like to be able to calculate it. So to do that, we will work today with fixed currency rates. Yeah, so we get the same answer, and usually in an exam they will tell you the currency rate. You don't have to remember anything. They will tell you all the information you need to solve that question. So let's have a look at this example. Given that $1 equals to 0.7 pounds, right? I want to find how much does 3.5 pounds equal to in dollars. Or to put it in other words, how many dollars will 3.5 pounds buy? So in order to find that, we already know the relationship between dollars and pounds. We can use the ratio method. This is a method I really like to work with in these type of questions. So I'm going to write down the ratio 1 to 0.7, and that's the ratio from, I'm going to write it down so it becomes more clear, from dollars to pounds. Right, and then now the new ratio is that we know the pound is 3.5 and we want to find the dollars, so we're going to let that be x. In order to find the value of x, which is how much dollars 3.5 pounds will buy, we can do 3.5 divided by 0.7 multiplied by 1. The reason that we do this is because when we do 3.5 divided by 0.7, we will get a relationship between these two ratios, because these two ratios, I'm going to mark it out to let it be more clear. Ratio here and the ratio here, they are comparing the same things. They're comparing dollars to pounds. Both of them are. So if I multiply 0.7 by a number, I will get 3.5. And if I multiply 1 by that same number that we multiplied 0.7 by, we should be able to get the correct corresponding value of x. So I'm going to do that right now. I will get 5 multiplied by 1, and that is just 5. So my final answer is 3.5 pounds equals to $5. Right, and that's done with this problem. Let's look at a slightly more difficult one. It's actually not like so difficult, it's just more steps and more complicated ratios. Now, $1 equals to 6.57 yuan, and $1 equals to, I'm going to try and write this symbol, it's a bit hard for me. Okay, 67.79 rupee. Alright, and then I want to find how much rupees I can buy with 50 yuan. How much rupees can I buy? I'm going to put a question mark here. Or we can let it be x actually. Let's let it be x. Again, we will use the ratio because that's the easiest way to find these type of questions. It will be 6.57. Since both of them, both this and this, they equal to $1, so we can equate them and end up with this ratio, 6.57 to 67.79. And that's the ratio from yuan to rupees. Now, we know that yuan is 50 and rupee, the corresponding to 50 yuan, is x. So I'm going to write x here. Again, like we did for our last question, we're going to still do division, then multiplication. We're going to find the relationship between 50 and 6.57. So this number, this number here and this number here. So I'm going to do 50 multiplied by 6.57. And then multiply this number by 67.79. Because when you multiply 6.57 by a number and then you get 50, if you multiply that same number by 67.79, we should be able to get the corresponding rupees to 50 yuan. So I'm going to enter that into my calculator Right now, 50 divided by 6.57 and multiply that by 67.79, I will end up with 515 point, a lot of decimal points that follows. But when you're working with currencies, and if the question doesn't state to put it in 3 significant figures or 2 decimal places, always put your answer in 2 decimal places. If the question is not really clear, 2 decimal places, that would be 9, 1, right? And the unit, don't forget to put, is rupees. Now I should be able to write it in front, but I don't have any space here. The last topic of numbers are rational and irrational numbers. So I'm going to write rational. To identify whether a number is rational or irrational number, the best way is to think like rational numbers are normal numbers, but irrational numbers are psychopath numbers. So this will help you to remember them, but a more, let's say, professional way to say it is that a irrational number is a number that cannot be written as a fraction. So assume that we have the number square root of 2. Can square root of 2 be actually written as a fraction? Well, the answer to that is no, because a real fraction have to have its numerator and denominator both as integers, and square root of 2 is not. If you enter square root of 2 onto your calculator and convert that into a decimal, you will get a bunch of decimal like 1.414213 and so on, without actually getting any patterns, right? We don't get any pattern from 414213. There's no patterns. Therefore, square root of 2 is an irrational number. So it's the same as for the number pi. Pi is 3.14 and so on, without a pattern. So whenever we get a number, when you transfer that number into a decimal and there is no pattern with the decimals, that is irrational. It's actually very easy to remember in this way. So you really need to know the difference between rational and irrational numbers. And even to help you a little bit more, we're going to draw a Venn diagram, right? Just to get your head clear around different type of numbers, and there are quite a few. So the widest range is R. I'm not really sure if I can draw the symbol. I'll try my best. Okay, something like that. Symbol R. This is real numbers. Real numbers. Right, numbers is in the shorter form. And this Q looking like shape, that's a Q. Right, by the way, if you don't recognize. And this represents rational numbers. And Z represent integers. So integers can be both positive or negative. So let me give you a couple of examples. Let's say -1, 0, 1, and 2. They are enough to represent enough patterns. And then lastly, we have N, which represents natural numbers. Now, a lot of people get confused with natural numbers and integers. So a good way to distinguish between those two is to think natural numbers are positive integers, whereas integers by itself can be both positive or negative. I'm going to write as a little note here, positive and negative. But for natural number, it can only be
positive. Or some people can call like natural numbers as being positive integers. So they write it as Z with a plus sign at the top. It represents natural numbers. So let me give you guys an example of natural numbers. It would be 1, 2, 3, and so on. This is actually easy to remember from the word natural, because natural is meant by like the natural way of doing something. So when you go and count, let's say you want to count the amount of pencils you have, you're going to start counting from 1, right? You're going to say 1, I have 1 pencil, 2 pencils, 3 pencils. But you do not start counting from 0. So the first natural number is 1. Right, and that's all the numbers we have.
Now here is a Venn diagram which can help you guys to visualize the relationships between those numbers. So in the biggest range, it is the real numbers. So any number that you can find, they are real numbers. And then it comes the rational numbers. So most of the real numbers are rational numbers, but there can also be irrational numbers. Now you may ask, why are there no place in this Venn diagram for irrational numbers? Well, if we were to have to draw an irrational number onto this Venn diagram, then it should be somewhere here in a separate set from the rational numbers. So over here, I'm gonna color this. Yeah, here it is. So then inside the rational numbers, they are the integers. That means any integers are rational numbers. Well, it makes sense because every integer can be put as a fraction. And then every integer is a rational number. Every rational number is a real number. That means every integer is also a real number. Right, and then in the middle we have natural numbers. Natural numbers are positive integers, and positive integers are surely integers. So natural numbers are integers, and integers are rational numbers, and rational numbers are real numbers. So that gives us a conclusion that real numbers are the widest range, and real numbers can include rational and irrational numbers. And inside those rational numbers, we have integers, and inside those positive integers, we have also got, and inside those integers, we've also got positive integers. And that's it. Now we will move on to look at some numbers, and we will identify whether they are rational numbers and irrational numbers. Let's see. Let's say we'll first start by looking at a simple one. 0, oops, that's too thick. Okay, 0.785. Is this number an irrational number or a rational number? Well, this number can be put as a fraction for certain. It can be written as 785 over 1,000. Right, if you multiply 0.785 by 1,000, you will get 785. So it can be put as a fraction, therefore it is a rational number. Now, the next one. Let's say now we have the number 0.67 repeating. So that means it's 0.676767 and so on. Well, we learned how to convert an reoccurring decimal into a fraction, right? We let this be x. Then we go and find 100x, which is that multiplied by 100. So we get, I'm going to rewrite this equal sign, 67.67 repeating. Then we're going to do subtraction between those two. So 100x minus x. That means 67.67 repeating minus 0.67. So I will end up with 67. The recurring decimals got removed. And then we have 99x equals to 67. So x equals to 67 over 99. And 67 over 99 is the fraction form of the 0.67 recurring decimal. And this number again can be put as a fraction. Therefore, it is a rational number. Now let's move on. Square root of 2. Can square root of 2 be put into a fraction? Obviously cannot. So this one is an irrational number. How about now I change this question a little, and then I say square root of 2 multiplied by square root of 2. Well, if we multiply two square root together, we will get them inside the same square root. And that will give us square root of 4, which give us the number 2. So number 2 is an integer. And integers are rational numbers, right? If you refer back to the Venn diagram that we looked at. Just going to quickly go there. Yeah, so integers are represented by the letter Z. And Z is part of a rational number. Alright, now we're good to move on to some real questions. Let's see. If you have a question that says, find me a rational number between square root of 2 and square root of 3. What's the thing that you will do? Now, you first of all have to see where square root of 2 lies on the number line and square root of 3. And in order to do that, we are trying to find like square root of 2 in decimals. So if you enter that into your calculator, square root of 2, it will give us 1.4142, and we're gonna stop there. And square root of 3 would give us 1.73205, and so on. I'm gonna stop there. In order to find a number in between, we need to find a number. Let's call that number x, bigger than that number but smaller than this number. So any terminating or recurring decimal between these two numbers will be rational, and that's what we're trying to find, a rational number between square root of 2 and square root of 3. So let's say 1.5. It would do 1.6 or whatever. Let's go for 1.5. And that's done. Now we will look at surds. So you can see surds as a root that is irrational. So let me give you guys a couple of examples. Square root of 3, square root of 7, square root of 11. These are 3 examples of surds, and you will notice a common thing between these 3 numbers, which is the number under the roots are 3, 7, and 11, and all these 3 numbers are prime. So we come into a conclusion that the roots of a prime number are surds. So let's look at one number that also have a root but is not a surd. That is square root of 4 or square root of 9. These 2 numbers are not surds, because 4 and 9, they are not prime numbers, so we have to cross these 2 out. Alright, and then we will come to look at 2 simple rules which you need to know in order to simplify surds. So the first rule is square root of a multiplied by b can be simplified to just square root of a multiplied by square root of b. You can separate them like that. So the second rule is square root of a over b equals to, you can also separate that, square root of a divided by square root of b. So in cases of multiplication, which is in the first case, and in case of division in the second case, you can separate the roots and then still get the same answer. So let's have a look at an example. If I want to write, let's see, square root of 8. If I want to simplify this square root of 8, then what I will do, what I will do is I'll separate 8 into 2 times 4. Yeah, and then I can take out the 4, so it will become square root of 2 multiplied by square root of 4. And then you will know that square root of 4 is 2, right? And square root of 2 multiplied by 2 would finally give me an answer of, okay, I'm gonna write it here. Square root of 2 square root of 2. Yeah, so square root of 8 can be simplified to 2 square root of 2 by using the first rule. Alright, and it's pretty similar with the second rule, just with division. Now let's move on to something slightly different, which is 3 more rules. 1, 2, 3, which I'm going to write down. And these 3 rules are used to manipulate sets. That is, if we know these 3 rules plus the 2 rules that we learned before, we can actually go and solve some problems involving sets, like square root of 2 plus 4 square root of 2. Questions like that. So let's take a look at those 3 rules. A over square root of b multiplied by square root of b over square root of b. That's our first rule. I don't have space here. I'm going to write the second rule here. Second rule is 1 over a minus square root of b multiplied by a plus square root of b over a plus square root of b, which is actually 1. You'll see in a moment. I'll explain it once I wrote all these 3. 1 over a plus square root of b multiplied by a minus square root of b over a minus square root of b. So what's common to all these 3 rules is that the second part all equal to 1. And we know that when we multiply any number by 1, we will still get that original number. So that means we did not do anything. But the reason that we will multiply it by square root of b over square root of b, and a plus square root of b, and a plus square root of b, and a minus square root of b over a minus square root of b is to get rid of the roots in the denominator. If you go and look at example 1, so a over square root of b, that one, we will see that when square root of b multiplied by square root of b, it's the denominator, and numerator is a multiplied by square root of b. You will realize that the denominator will not have any roots anymore. Before it was square root of b, before it was multiplied by square root of b over square root of b. While after that, you will get square root of b squared, yeah? We know that square root of b can be multiplied by square root of b by putting them into the same root from the previous rules that we looked at for simplification. And then the numerator will still have a root, and that's okay, because we only want to get the denominator free of roots, right? If that makes sense. Just like for question 1, for example 1, example 2 and 3 are similar. You will see that that's a completing square. So a minus b square root of b times a plus square root of b is basically a squared minus square root of b squared, right? And then once you simplify this, you get a squared minus b for the denominator for the second rule, right? And there's no roots. And then same for question 3, we will get a squared minus b again, just like for the second question. So let's actually go and look at some examples working with those. Let's say now we have, which one shall we do? 6 over square root of 3. I want to write this as a third. So a third, let me just remind you of its definition, is a irrational root. That means the number under the root is a prime number. So it looks something like this, square root of x, which x is a prime number, but we can also have a number in front. So let's say y multiplied by square root of x. We can have that, and that's still a third. So let's have a look at an example, this example. So we said that we're trying to get rid of the roots in the denominator, right? So what we're going to do here is to apply the first root. So we're going to multiply this 6 over square root of 3 by 1. And in this case, it would be square root of 3 over square root of 3. Because when square root of 3 multiplied by square root of 3, we get just 3. And for the numerator, we get 6 square root of 3. We can simplify that further, because 6 divided by 3 is 2. So 2 square root of 3 will be our final answer. Alright guys, and now we will look at a new chapter called sequence. So to start off with, we're gonna look at a nice and easy example. Finding the difference between different terms of the sequence, so we can find the next few terms of the same sequence. Let's go straight into an example. Let's say we have 2, 5, 10, 17. And then it asks you to find the next term, the fifth term. So in order to do that, we can find the relationship between each term. 2 plus 3 equals to 5, 5 plus 5 equals to 10, and 10 plus 7 equals to 17. Now we go and find the relationship between these three numbers. So from 3 to go to 5, we add 2. And from 5 to go to 7, we add 2 again. So now we've came up with the common difference, which is 2, right? And then to find the fifth term, we just do another loop. This would be plus 2 again. So 7 plus 2 will give us plus 9. And then 9 plus 17 will give us 26. So the fifth term equals to 26. And that's it. Let's go now and look at a formula of a sequence. Now, to find the formula of a sequence, you need to first understand what that equation represents. So let's go and look at an example. 40, 38, 36, 34. If you want to find a formula for the nth term of the sequence, the formula will have this form, an plus b, in which n are just different terms. So if we want to find the first term, n will be 1. If we want to find the second term, n will be 2. So n will always start as 1. Alright, and the number a here will represent the common difference, actually. First of all, I'm going to find the difference. 40 to go to 38, we minus 2. From 38 to go to 36, we minus 2 again. 36 to go to 34, we minus 2 again. So that's our common difference, negative 2. Therefore, we get negative 2n plus b.
but we do not want an unknown there. We want to change b into a number, a real number. So what should it be? But if you think back, we referred to n will always start with 1. Therefore, we know the first term, second term, third term, and fourth term. If we substitute any of these 4 values inside this formula, then we should be able to find b. So let's try and do that now. Let's substitute n to equal to 1. So we're working with the first value, 40. And then -2 times 1 plus b equals to 40. So -2 plus b equals to 40. b can be solved, and b equals to 42. Right, and the final formula, I'm going to write it out here, is a is what? -2 and plus b is 42. So that's our final answer. And that brings us to the end of this whole big topic with numbers. And if you have any suggestions, please leave in the comments down below. Subscribe to my channel if you want to see more videos like this, and see you!